12,000 light-years away in the quiet darkness of the Aquila constellation, an ancient star is doing something that breaks our basic understanding of celestial peace. It is not shining gently upon the world it created millions of years ago. Instead, it is dragging a massive gas giant down into its glowing fire, ripping away its atmosphere and consuming it piece by piece. We are watching a parent star eat its very own child. If you love uncovering real cosmic mysteries without fake hype or exaggerations, hit that subscribe button right now to join our community of space explorers. We break down the most incredible, mind-bending truths about our universe every single week. For generations, human beings looked up at the night sky and imagined stars as calm, permanent guardians of the world circling around them. When we look at our own sun, we see a steady, warm ball of light that gives us life, anchors our planet in a perfect circle, and allows plants, oceans, and people to flourish. We naturally grow up believing that a star and its planets form a peaceful family that stays together in perfect harmony forever. In school textbooks, planetary systems are almost always shown as neat, clean, clockwork mechanisms. The central star stays perfectly positioned in the middle, while the planets trace out smooth, unchanging paths around it for billions of years. Astronomers once believed that once a system forms from a spinning cloud of gas and dust, its layout is practically frozen in stone until the very end of time. That comforting picture was completely shattered when a team of astronomers pointed powerful sky-scanning telescopes toward a distant patch of our galaxy. What they captured was not a quiet, orderly dance of planets. It was an active, violent cosmic feeding ground where an aging star was caught in the middle of swallowing an entire world whole. To understand how such a violent event can happen, we have to look closely at how stars live, change, and eventually die. A normal star spends the vast majority of its long life burning hydrogen gas deep within its superheated core. This burning process is called nuclear fusion, and it creates an enormous outward blast of pressure that fights directly against the heavy inward pull of gravity. As long as a star has plenty of hydrogen fuel to burn in its center, these two powerful forces remain locked in a perfect, balanced stalemate. Astronomers call this long, peaceful chapter of a star's existence the main sequence. Our own sun is right in the middle of this stable phase, where it has been quietly burning for nearly 5 billion years without any sudden, catastrophic disruptions. During this peaceful main sequence era, planets enjoy a stable climate and a predictable orbit around their star. The star's energy output changes only very slowly over billions of years, giving life the long stretches of time it needs to develop, evolve, and spread across a planet's surface. For billions of years, the relationship between a star and its planets looks like a permanent partnership. However, hydrogen fuel does not last forever in a star's core. Deep inside the center of the star, billions of tons of hydrogen are converted into helium every single second. Eventually, after billions of years of relentless nuclear reactions, the hydrogen at the very center runs out completely, leaving behind an ash heap of dense helium. When that vital fuel supply is gone, the delicate balance between gravity and outward energy breaks down in an instant, and gravity immediately takes control. Without outward pressure pushing back, the heavy core begins to collapse inward under its own crushing weight. As the core shrinks tighter and tighter, it gets unimaginably hot and dense, sparking a new wave of intense burning in a thin shell of gas just outside the core. This sudden surge of new heat acts like a blowtorch, pushing the outer layers of the star violently outward into space. The star begins to puff up like a massive, glowing red balloon, growing dozens or even hundreds of times larger than its original size. Astronomers refer to this bloated, swollen phase as a red giant star. As the star expands, its fiery outer surface sweeps across millions of miles of empty space, moving steadily closer to any planets that orbit nearby. The glowing boundary of the star swallows up the empty distance between worlds, changing the once peaceful planetary system into an inescapable cosmic furnace. For decades, theoretical scientists had predicted through computer models that expanding red giant stars must occasionally run into their inner planets. But there was a major puzzle that left scientists deeply frustrated and unsure. Despite decades of searching through billions of stars across the sky, no astronomer had ever actually caught a star in the very act of eating a planet. Many astrophysicists assumed that catching such an event was practically impossible because space is so vast, and the final moment of planetary destruction was thought to be very fast and quiet. They believed a planet plunging into a giant star would be like a tiny single drop of water falling into a roaring forest fire, disappearing without leaving behind any clear trace for our telescopes to detect. They calculated that the actual engulfment event might only produce a brief, invisible ripple beneath the star's glowing surface. Because the star is already millions of times larger than the planet, the added material was expected to vanish quietly into the churning sea of gas without making any visible noise or light that human telescopes could ever spot from thousands of light years away. That common belief turned out to be totally wrong. In May of 2020, an automated robotic telescope located in the mountains of California, known as the Zwicky Transient facility, detected a strange, sudden flash of light coming from the constellation Aquila. The mysterious flash of light was cataloged by astronomers under the code name ZTF SLRN 2020. When the sky scanner first logged the bright flash, the computer system automatically flagged it as a normal stellar flare, which is a common, short burst of magnetic energy on a star's surface. But as researchers began looking more carefully at the exact colors and wavelengths of the light, they realized something was deeply abnormal about this particular event. The flash was not blazing white hot like an exploding supernova or a typical magnetic outburst. Instead, the data showed that the event was strangely cool, giving off most of its energy in long red and infrared wavelengths. An astrophysicist named Kishle Day at the Massachusetts Institute of Technology decided to investigate the strange event more closely using infrared space observatories. At first, the research team thought they might be looking at two full-size stars crashing into one another, an event known as a red nova. But when they calculated the total amount of energy released by the flash, the numbers simply did not match up with two stars colliding. The energy output of this flash was roughly 1,000 times smaller than any stellar merger ever recorded in human history. That critical difference in energy led researchers to an astounding conclusion. The object that had crashed into the giant glowing ball of gas was not a second star at all. It was an object roughly the mass of Jupiter. For the very first time in astronomical history, humanity had captured real-time evidence of an ancient star consuming a planetary companion. Did you ever imagine that an entire planet could be swallowed whole by its own sun and leave behind a glowing flash of light? Tell us your thoughts in the comments below, and hit the like button if you love learning about real space discoveries. When scientists reconstructed the timeline of what actually happened during those final months, the details revealed an incredibly intense physical drama. The doomed world was a gas giant, a massive world made primarily of thick hydrogen and helium gas, orbiting dangerously close to its host star. It was the kind of planet astronomers classify as a hot Jupiter. Long before the final plunge, the planet had already been circling its star at an extremely close distance, completing a full orbit in just a few Earth days. As the aging parent star began its slow red giant expansion, its thin, wispy outer atmosphere began to brush against the outer edge of the planet's orbital path. This thin halo of stellar gas created a powerful braking effect known as orbital drag, acting like a continuous wall of friction pushing against the moving world. Because the planet was constantly pushing through this glowing fog of gas, it began to lose its forward speed. As its orbital speed dropped, gravity pulled the planet into a tighter, inward spiraling death dive toward the star's surface. Here is the detail that scientists found most fascinating. This destruction was not an instantaneous crash that happened in a single second. It was a slow, agonizing process where the star's immense gravity gradually tore the planet out of shape. Because the side of the planet facing the star was closer than the backside, gravity pulled much harder on the front half. These uneven gravitational forces, known as tidal forces, stretched the round planet into a distorted, egg-like shape. The star acted like a giant cosmic vacuum cleaner, stripping the outer layers of hydrogen gas right off the doomed world and pulling the stolen material into a glowing, swirling bridge of fire between the two bodies. As the planet was pulled closer and closer, the extreme friction created violent shock waves throughout its atmosphere. The upper layers of gas reached temperatures of thousands of degrees, causing the planet to glow like a second miniature star as it plunged deeper into the surrounding envelope of stellar gas. To see what was happening through the thick dust, astronomers analyzed infrared data collected by NASA's NEOWISE space telescope, which had been scanning that same region of the sky for years. The infrared records revealed that as gas was ripped from the planet, large clouds of matter were blasted outward into deep space, where they rapidly cooled down and condensed into thick clouds of dark cosmic dust. This surrounding cloud of dust began glowing brightly in invisible infrared light, giving away the crime scene long before the core of the planet met its final end. For nearly 9 months, the stripped core of the planet skimmed through this blistering outer atmosphere of the star, heating up to thousands of degrees until its internal structure could no longer withstand the pressure. Then came the final catastrophic moment. The remaining heavy core of the planet plunged straight down into the dense, churning layers of the star, dumping all of its stored gravitational energy directly into the stellar furnace. That sudden injection of raw power caused the star to swell up to 4 times its normal size and brighten by more than 100 times within a few short days. For about 10 days, the bloated star burned with an intense, swollen fury as it completely digested the material of its dead planetary companion. Once the planetary material was fully dissolved and mixed into the churning gas of the star, the bright flare began to fade away, leaving behind a cold, expanding shell of glowing dust drifting quietly through space. The scientific world was completely stunned by how clearly this single event played out across multiple telescopes. It proved that planetary engulfment is not a quiet, silent disappearance, but a dynamic, explosive event that reshapes the star and leaves behind glowing signatures across the electromagnetic spectrum for months. What makes this discovery even more chilling is the realization that ZTF SLRN 2020 is not some rare freak accident that happened only once in our galaxy. Astronomers have identified several other extreme planetary systems where this exact same process is happening right now in real time, including a famous scorched world known as WASP-12b. WASP-12b is an enormous gas giant located about 870 light-years away from Earth in the constellation Auriga. It orbits so close to its parent star that a full year on that planet takes just 26 Earth hours. Because it is practically skimming the star's surface, the planet is heated to an astonishing 2,700 degrees Celsius. At such extreme temperatures, rocks do not exist as solid ground. They vaporize into gas, clouds are made of liquid metal, and the night side of the planet glows like burning charcoal. The intense gravitational pull of the host star has already stretched WASP-12b into an egg shape, and the star is actively siphoning away nearly 1 Earth mass of gas every 30,000 years. Astronomers measuring the orbit of WASP-12b with extreme precision have found that its orbit is shrinking by a tiny fraction of a second every single year. Scientists calculate that the planet has only about 10 million years left to live before it is dragged down into the star's outer layers and swallowed completely. In the cosmic timescale of the universe, 10 million years is just a tiny blink of an eye. Another terrifying example is the planetary system known as KELT-9b, which orbits a massive, blazing blue star that burns twice as hot as our Sun. KELT-9b is so hot that the intense radiation from its star is literally boiling its atmosphere away into empty space, creating a long, glowing tail of gas that stretches behind the planet like a giant comet. The star is blasting the planet with so much high-energy radiation that molecules cannot even hold themselves together in its sky. Water, methane, and carbon dioxide are completely torn apart into raw individual atoms, and heavy metals like iron and titanium float as glowing vapors in the upper atmosphere. Scientists watching KELT-9b believe that the planet is being stripped down to its bare rocky or metallic core, a process known as photoevaporation. If the planet does not get completely destroyed by radiation first, its decaying orbit will eventually pull whatever is left of its skeleton directly into the blazing blue furnace of its parent star. In another distant system known as HD 2004-58b, often called OSIRIS, astronomers use the Hubble Space Telescope to watch an enormous cloud of hydrogen, carbon, and oxygen streaming off the planet. The star's intense stellar wind is blowing this material away at speeds of tens of thousands of miles per hour, acting like a cosmic blowtorch that slowly chips away at the planet day after day. Astronomers also look closely at systems like Kepler 1658b, where a planet orbits an evolved subgiant star. Detailed timing data gathered over more than a decade showed that this planet's orbital period is steadily decreasing by about 130 milliseconds every year. It is spiraling into its doom, providing direct proof of orbital decay in real time. Have you ever wondered what it would look like to stand on a planet where the sky is filled with glowing, vaporized metal? Drop your reaction in the comments below, and make sure to subscribe if you want to keep exploring the wildest corners of the universe with us. While watching these distant planetary deaths provides incredible scientific insights, there is a much bigger and far more personal question behind this entire field of research. What is going to happen to our own solar system when our sun finally reaches the end of its life and begins to run out of hydrogen fuel? For a very long time, school textbooks taught students that the sun would expand in about 5 billion years, turning into a red giant and easily swallowing Mercury and Venus. But when it came to Earth, scientists were split into two completely different camps of thought, and a fierce debate raged for decades. One group of astronomers believed that as the sun ages and expands, it will lose a significant amount of its total mass by blowing strong solar winds out into space. Because the sun would become lighter, its gravitational grip on the planets would weaken, allowing Earth's orbit to slowly drift outward to a wider, safer path before the solar surface could reach us. According to this optimistic view, Earth would move outward toward the current orbit of Mars, staying just far enough away to avoid the advancing wall of solar fire. Our planet would still become an uninhabitable, scorched desert, but the physical rock of Earth would survive as a charred monument to human history. However, the second group of researchers argued that this outward drift would not be fast enough to save our planet. They calculated that the tidal drag caused by the sun's expanded outer atmosphere would overpower any outward drift, slowing Earth down and dragging it inward just like the doomed planet in the Aquila constellation. The direct real-world observations from the ZTF SLRN 2020 event have provided powerful evidence that supports the darker, more destructive theory. The data showed that a star's thin outer gas layers reach much farther out into space than previous models predicted, creating immense friction that easily captures nearby orbiting worlds. When our sun begins its final red giant expansion billions of years from now, The process will unfold slowly over millions of years, but the outcome will be entirely unstoppable. The sun will gradually swell in size, glowing with a deep, menacing reddish-orange light that will completely transform the environment of the entire inner solar system. Mercury will be the very first world to disappear into the glowing wall of solar plasma, followed shortly after by Venus, whose thick clouds of carbon dioxide and sulfuric acid will instantly boil away into the burning solar furnace. Then, the expanding edge of the sun will set its sights on Earth. Long before the glowing surface of the sun actually reaches our planet's orbit, life on Earth will have become completely impossible. As the sun grows hotter and larger in the sky, the intense heat will cause Earth's oceans to boil, filling the atmosphere with superheated steam before all water is permanently lost to space. The continents will dry up into vast, lifeless deserts of cracked stone, and eventually the surface rock will begin to melt, turning mountain ranges into flowing rivers of red-hot magma. The atmosphere will be stripped away by the fierce solar wind, exposing the molten crust directly to the searing heat of the approaching star. When the sun's outer gas finally reaches Earth's orbit, our planet will begin skimming through the blistering solar atmosphere, experiencing the exact same relentless braking friction that destroyed the gas giant in Aquila. Earth will be pulled into a decaying spiral, drawing closer to the sun's center with every passing orbit. Eventually, our home planet will plunge straight down into the churning interior of the sun, vaporizing into basic elements and dissolving completely into the solar mass. To an alien astronomer watching from a telescope thousands of light years away, the complete destruction of our world and everything humanity ever built will look like nothing more than a tiny, gentle infrared flash lasting just a few days. After consuming Earth, the sun may continue its expansion toward the orbit of Mars. While Mars might escape direct engulfment because of its greater distance, its thin atmosphere will be completely blown away, and its red surface will be baked into a blackened, glassy crust by the overwhelming solar radiation. The outer giant planets, including Jupiter, Saturn, Uranus, and Neptune, will watch this destruction from a safe distance. Their icy rings will evaporate, their moons will melt, and their outer atmospheres will heat up, but their massive distances will keep them safe from the sun's hungry grasp. Do you think human beings will develop the technology to migrate to another star system before our sun reaches its red giant phase? Share your predictions in the comments below and give this video a thumbs up if you find the future of our solar system thought-provoking. The realization that stars regularly swallow their planets has opened up an entirely new way for astronomers to study the history of our galaxy. Scientists do not have to wait around, hoping to catch a star in the exact 10-day window when it is swallowing a planet. They can look for the chemical evidence left behind inside the star long after the meal is over. When a star is born, it is composed almost entirely of light gases, mainly hydrogen and helium, with only tiny traces of heavier elements. Rocky planets like Earth, Mercury, and Mars, on the other hand, are packed full of heavy elements such as iron, magnesium, silicon, aluminum, and nickel. When an aging or unstable star swallows a rocky world, those heavy elements do not sink immediately to the core. Instead, they remain suspended in the star's outer churning layers for millions of years, acting like a chemical fingerprint of planetary cannibalism that astronomers can detect using a technique called spectroscopy. By breaking a star's light down into a detailed rainbow spectrum, astronomers can see dark lines that correspond to specific chemical elements present in the star's atmosphere. If a star shows an unusually high concentration of iron, lithium, and refractory metals that match the composition of rocky planets, scientists know they are looking at a star that has eaten one or more of its own worlds. Lithium is a particularly famous clue in this chemical detective work. Normal stars destroy their lithium very early in their lives because lithium burns at relatively low temperatures inside stellar interiors. If an older star has an abnormally high amount of lithium on its surface, it almost certainly swallowed a planet that was rich in lithium. Recent large-scale surveys using powerful telescopes in Chile and the United States have examined thousands of twin stars known as co-natal stars, which were born from the exact same cloud of gas at the same time. Because twin stars start with identical chemical mixtures, any major difference in their composition today reveals what they have consumed over their lifetimes. The results of these massive surveys shocked the scientific community. The data revealed that roughly 1 out of every 12 stars in our galaxy shows clear chemical evidence of having swallowed a planet. That means planetary cannibalism is not an extraordinary exception to the rule. It is a routine, common event in the life cycle of stellar systems. When you multiply that fraction across the more than 100 billion stars that make up our Milky Way galaxy, the numbers become truly staggering. Tens of billions of planets across our galaxy have been pulled from their orbits and destroyed by the very stars that gave them life. This discovery has completely upended the old idea that solar systems are stable, permanent structures. Instead, Planetary systems are dynamic, constantly changing environments, where gravitational forces can shift, orbits can destabilize, and worlds can be completely erased over cosmic timescales. Astronomers have also discovered that planetary destruction does not only happen when a star grows old and expands into a red giant. A star can also consume its planets when it is very young, during the chaotic early days when the planetary system is first forming. In a young solar system, dozens or even hundreds of baby planets compete with one another for space and material inside a thick, swirling disk of leftover gas and dust. The strong gravitational tug-of-war between large gas giants can easily fling smaller, rocky planets out of their stable circular paths. Some of these displaced planets get violently kicked entirely out of the solar system, becoming lonely, frozen rogue planets that drift through interstellar space forever. But many others get thrown inward, sending them on a direct collision course with their young host star, which swallows them long before the system ever has a chance to settle down. Computer simulations of our own early solar system suggest that Jupiter and Saturn may have migrated inward and outward during their early years, a theory known as the Grand Tack hypothesis. During this chaotic migration, Jupiter's immense gravity may have swept several early super-Earth planets straight into the young Sun, clearing the way for Mercury, Venus, Earth, and Mars to form later from the leftover debris. Did you know that our own Milky Way galaxy contains billions of stars that have already eaten their own planets in the past? Tell us what you find most surprising about this fact in the comments, and be sure to subscribe to stay connected with our latest deep space stories. Scientists are now using the most powerful space observatories ever built, including NASA's James Webb Space Telescope, to investigate another fascinating mystery related to planetary death: the fate of planetary systems around dead stars known as white dwarfs. A white dwarf is the tiny, super-dense leftover core of a star that has finished its red giant phase and shed all of its outer gas into space. A typical white dwarf is about the same physical size as Earth, but it packs the entire mass of a normal star, creating an immense gravitational pull at its surface. Because a white dwarf has such powerful gravity, any heavy elements like iron or silicon in its atmosphere should sink straight down into its center within a matter of days, leaving the outer surface purely clean and made of light hydrogen or helium. Yet, when astronomers look at many white dwarfs with the James Webb Space Telescope, they consistently find heavy, rocky elements polluting the outer atmosphere. This means that even after a star dies and shrinks down to a tiny, glowing cinder, it continues to pull in and grind up the surviving outer asteroids, moons, and leftover planets that manage to escape its red giant expansion. Astronomers call this cosmic debris field a polluted white dwarf system, and it gives researchers a rare opportunity to study the internal chemical makeup of destroyed exoplanets. By analyzing the light from these polluted white dwarf stars, scientists can literally measure the chemical ingredients of rocky worlds that were torn to shreds millions of years ago. In several famous cases, such as the white dwarf designated WD 1145 Plus Original 117, astronomers have watched small rocky planetesimals actively breaking apart as they orbit the dead star every 4.5 hours. The star's gravity is ripping these objects into trails of dust that block out the star's light in irregular patterns. The data reveals that many of these destroyed exoplanets had internal structures and chemical balances very similar to Earth, containing iron cores, rocky silicate mantles, and even traces of water ice. It is a sobering reminder that worlds, just like our own, exist throughout the universe, but they are all subject to the relentless laws of gravity and stellar evolution. This emerging understanding of planetary death has major consequences for our ongoing search for extraterrestrial life. When astronomers search the sky for potentially habitable worlds, they typically search for planets located in what is known as the habitable zone, or the Goldilocks zone. The habitable zone is the sweet spot around a star where the temperature is just right for liquid water to pool on a planet's surface, neither too hot nor too cold. But our new discoveries show that a star's habitable zone is not an unchanging, permanent location in space. As a star slowly ages and brightens over billions of years, its habitable zone continuously moves outward into the solar system. A planet that starts out in a perfect, life-friendly orbit during the star's youth will eventually find itself baked by unbearable heat as the habitable zone drifts past it. Conversely, cold, icy moons and frozen planets orbiting far out in the system, such as Jupiter's moon Europa or Saturn's moon Titan in our own solar system, might temporarily thaw and become warm, ocean-covered worlds as the star expands in its old age. However, this late-stage habitable phase around an expanding star does not last long enough for complex life to evolve from scratch. It creates a fleeting window of warmth that lasts only a few million years before the bloated star either engulfs those outer worlds or sheds its outer layers and cools down into a faint white dwarf. Astronomers must also consider the dangerous radiation bursts that occur when planets fall into stars. The energy released during an engulfment event can strip the atmospheres of neighboring worlds, potentially destroying any delicate biosphere that was trying to survive on a world farther out in the system. The story of stars feeding on their own planets reminds us of the delicate balance that makes human existence possible in the first place. Our sun is currently in the prime of its life, providing a remarkably steady, unchanging source of energy that has allowed life to evolve from simple single-celled organisms into complex creatures capable of building telescopes and exploring the cosmos. We are living during an exceptionally fortunate golden age of our solar system, positioned in a quiet window of time between the chaotic, violent collisions of planetary youth and the unavoidable destruction that awaits in the sun's distant old age. Every time we point our instruments into deep space and witness the violent death of a distant world, we gain a deeper appreciation for the fragility of our own home planet. Earth is a rare, beautiful oasis of life drifting through a vast cosmic wilderness where stars are born, consume their creations, and fade away into the dark. Understanding the ultimate fate of our world does not mean we should look at the universe with fear. Instead, it fuels our curiosity to explore further, build better technology, and perhaps, one day, carry the light of human consciousness beyond the boundaries of our original solar system. If you enjoyed this deep dive into the hidden mysteries of the universe, please take a moment to subscribe, turn on all notifications so you never miss an upload, share this video with a friend who loves space science, and let us know in the comments, do you think humanity will find a way to escape our solar system before the sun expands? Thank you so much for watching, and we will see you in the next exploration.